Determine the force in members AF, BF, and BC and state if the members are in tension or compression. Okay, so we have a structure here, a truss structure, and it is kind of in the form of a vertical cantilever structure. It's pinned at point A, and it has a roller support at point B here, and it's subjected to some lateral forces. A lateral concentrated force at point E, 4 kilonewton here, and an 8 kilonewton at point F. Okay, so we're going to solve this problem by using a method of sections. So, method of sections. As you know, the truss analysis can be carried out by using either a method of joints or a method of sections. So method of sections is kind of a practical way of solving for the forces of truss members relatively easily compared to method of joints, where you need to write equilibrium equations at each and every joint to successfully find the member forces. Okay, so we are asked to find here the forces AF. So force AF, BF, this diagonal member, force in this diagonal member, and BC, this member. So what are the forces? And we need to state if they are tension, subject to tension, or subject to compression. Okay. So in the method of sections, we are using an imaginary cut to find these forces, and that imaginary cut here will be applied by passing like a vertical, like a horizontal imaginary cut, and write equilibrium equations either on one side or the other side of the truss, of the whole truss structure. So here we have applying this imaginary cut here, we have either up here this portion of the structure or this portion of the structure where we can write equilibrium equations, including the sum of the forces in the x direction and y direction, and also moment about a point. Okay, so we need to decide up or down. Okay, so considering these support reactions, okay, so we need to find the support reaction. If we decide to use the lower portion of the cut, then this means that we will need to find the support reactions here. But if we use the upper portion of the cut, then we will not have to find any support reactions. So let's, in this case, go ahead and choose the upper portion. Okay, so we use the upper portion. Okay, so choosing the upper portion, choose the upper portion or part of the cut, if you like. Okay, therefore no need to find or calculate support reactions. Okay, that's why we are choosing the upper portion. Okay, so based on that, let's go ahead and draw the upper portion here. Okay, so the upper portion, we do some space here. Okay, so we have this member here, and proportion looks something like that. Okay, and then we have this cut here, this cut here, and the diagonal. We have a cut there. Okay, and on this upper portion we have the externally applied loads 4 kilonewton here, and another externally applied force 8 kilonewton here. Okay, and we have 2 meter and 1.5 meter. These are the lengths here, 1.5 meter wide, and this bit is 2 meter. Okay, and we are having point F here, and also down here we have points and point B down there. So the continuation of this upper portion, we need to draw like the continuation of that. Okay, and then we have continuation of this portion, and they meet at point B. Okay, so that's point B here, and this distance is also 2 meters. Okay, right, and what else? So we need to write the unknown forces on the member. So let's assume, okay, let's give this cut a name. Let's say this is cut AA. So we're talking about like a cut here, AA cut, and we have these forces applied on these members. F force AF, so down there we have point A. Okay, so we have, so these assumptions are like the directions. So we have a force FBF here, and we have, so force, this force is FBC, so 3 forces. Okay, so using this, also note that this is the angle. For this one, we're going to use a 3, that's 3, 4, 5 triangle here. Okay, because it's 1.2, 1.5 and 2, so it's 3, 4 and 5. Okay, so what's the strategy for finding these 3 unknown forces? This one, and this one. So taking moments around point B and then taking moments around point F could be one strategy to find FBC and FAF. Okay, so so let's say total sum of the moments that these forces are, all these forces are causing around point B is 0. Okay, so in this equation we're going to eliminate FBF and FBC, okay, because their extension is pointing towards, they're intersecting at point B, so they won't be in this equation. Only one unknown, FAF, will be in the equation. Okay, so FAF times 1.5, that's in the positive direction, taking moments around B, point B. Okay, FAF times 1.5, and that's counterclockwise positive, so that's why it's positive, FAF times 1.5, and minus 8 times 2 minus 4 times 4. Okay, so the externally applied forces, so that is equal to 0. So this equation gives me FAF equals 21.3 kilonewton, and since I find positive value, my initial assumption for the direction of the force is valid, so that's a tension member, FAF. Okay, so if I do the same moment equilibrium around point F in this case, so sum of the moments around point F counterclockwise positive is equal to 0. So in this equation, FBF and FAF will be eliminated, and I'll be left with FBC only. So FBC times 1.5, that's positive counterclockwise, and minus 4 times 2. 4 times 2, 8 won't be in this equation, only 4 times 2, so that's equal to 0. So my FBC will be equal to 5.33 so that's 5.33 kilonewton, and initial assumption was compression, so since I find a positive value, so that's compression. Okay, so as for a FBF, this diagonal force, so I can write sum of the forces in the x direction is equal to 0. So in this case, I'll be having 4 kilonewton plus 8 kilonewton minus the x component of that force, FBF times 3/5. That's the x component, horizontal component. That is equal to 0. So my FB force BF will be 20 kilonewton, and the initial assumption is compression here, so I find a positive value, so that will be compression. Okay, so that's the solution of this problem. I end up with the forces here for my members here, so I can write for my members here, so my member here, member AF, I have my member BF, so that's F and that's B, and I have my member BC here, so that's member BC. Okay, and I have as a result, these members, AF is under tension, so this member is under tension, and that tension is 21, so this one is 21.3 kilonewton, 21.3 kilonewton, so that's that. So my member BF is 20 compression again, so if I go up there, okay, let me try to write a better diagonal member here, so that's kind of my member BF, and that is under compression, and that compression is 20 kilonewton, so that's 20 kilonewton compression, so that's 20 kilonewton compression. Okay, and finally my member BC down there, so that's BC, that's under compression as well, and that is compression force here and the compression force here. Okay, so that's my member. So, and that compression force is 5.33 kilonewton. So that's 5.33 kilonewton. Okay. So that's tension, that's compression, and that's compression. This concludes the solution of this problem. Thanks for listening.